And I'm going to spend today talking a bit about the work I've done in the previous few years. And so I did my master's back in New Zealand on extreme moisture fluxes, and then the year after that I spent a year at the Scripps Institute of Oceanography working on extreme moisture fluxes on the west coast of the US. And so I sort of swapped hemispheres, and then I've come here after that to do my PhD. So hopefully by the end of this talk I would have convinced you that moisture flux is important. And this animation here is a prime example of how important it can be. This is December 2005. For those of you who remember December 2005, it was the most costly flood for the west coast of the US. San Francisco got about $3 billion worth of damage. And if you just watch these plumes of moisture coming through, there's one there, 31st, comes straight into San Francisco. And so we're going to talk a bit about where these plumes come from, the synoptic conditions that drive those, and there's some lessons we can learn about tracking them back through their life cycle. A few fun ideas there. But to start with, we'll talk about some of my work from New Zealand. And so I used to work in the glaciological research group in New Zealand, looking at snowfall and alpine mass balance, glacier mass balance in the Alps of New Zealand. And that's almost where the study of ARs in New Zealand comes from. The study of extreme moisture fluxes comes from we want to understand our snow and ice better, and so we looked at our moisture flux. So we'll talk a bit about that, a bit about flooding, and some MJO interactions if we get some time. There's some interesting work that's coming out of that. You can see we're not too far from those tropics. And then for the second half of the talk, we'll move back to the northern hemisphere, and we'll jump into those ideas of atmospheric river life cycles. Where are these storms coming from, and can we learn something from looking at them back through their life cycle? Does their genesis tell us anything about how damaging they might be further down the track? And we're going to, throughout the whole thing, the whole talk, we'll bring in ideas of insurance claims and how we measure damage and impact of weather systems, and how we can sort of look at our synoptic conditions based on some surface observation of human impact. So some fun, interesting ideas there. Plenty of people to thank here, because it's been a long history of work here, maybe 2 or 3 years by now, starting from my masters. The New Zealand team, Nicholas Cullen and Daniel Kingston from Otago, and then Peter Gibson and Jono from NIWA, which is the New Zealand equivalent of NOAA. So a few figures here come from them, the National Institute of Water and Atmosphere. You might have heard of them. And then there's the US team at Scripps, Marty Ralph, Mike DeFlorio, Tom Corinham, Alison Codbin, Guan and Dwayne Will-Liza from JPL as well, that will help me along the way here. And then more recently, a team from Europe helping with some of the Southern Hemisphere precipitation ideas, Ben Pole and Jonathan Wiley. So plenty of people, but it's a long history of work here. And my last 2 years here in Wisconsin have been funded through a Fulbright scholar from the US Department of State. So, just to situate ourselves, for those who don't know, New Zealand in the Southern Hemisphere here, right down the bottom, we're sort of the last landmass in the Pacific Ocean before you hit Antarctica. We're the same latitudinal band as LA to Portland. So if you think this could be LA and then this could be Portland, but we're flipped upside down here. So that might give you an idea of the sort of weather we get. It's pretty comparable. Although we're in the South Pacific, we're very temperate and maritime, so you cannot get too far from the ocean, and so our temperatures are always held down by that ocean. We don't get nearly as extreme summers and winters as we do here in Wisconsin. It's very mild all year round. 2 main islands, North Island, South Island, with a big mountain chain running the length of the South Island, our Southern Alps. And that's going to become pretty important as we start talking about the direction of our moisture fluxes. There's 5 million people here, which is less than the population of Wisconsin. And there's also a fair amount of ice in our mountains, and so we care about that snow and ice, and we'll talk a bit about that. You can see here in this aerial imagery from summertime some of that permanent snow ice fields through the Southern Alps there. Just for those who are interested, this is sort of the geological setup. We have this big fault line running across the country with the Pacific plate subducting under the Australian Indo plate here, and so we get this big subduction zone tilted across the country, which just forces up these Southern Alps here, and then we get our volcanoes up in the north. Sweet, and just to situate ourselves, here's Wellington, our capital city. That's where Ultra Jacinda likes to spend her time, and it's also where they make all our favourite movies. Lord of the Rings and Avatar, and a lot of the recent Marvel movies are all done in Wellington these days. Here's Auckland, so most of the country live up here. About 1/3 of the country live up in Auckland, the city of sails, for obvious reasons. I'm sure Ian would enjoy his time there. But it is on 50 dormant volcanoes, and so that has its own hazards to think about there. But about 1/3 of the country live north of this line here, and then about 1/2 of the country live north of it from about here. So most of the people are up here, then people are spread throughout. I come from down here in Dunedin, well known for its wildlife, plenty of penguins and sea lions and rugged coastlines facing south to Antarctica. It's nice and chilly. Sweet, and so interested in science. here's sort of a topographic map of the Southern Alps. You can see the dark grey there is about 1,000 metres above sea level, and our moisture comes northwesterly into that. And if you plot out the mean annual rainfall, that's what you get. You get rain in the mountains. You get this very stark gradient of precipitation, up to 4 metres a year in this distributed map, but individual weather stations can get 12 metres per year. That's 38 feet of rain, which is some of the highest rates that we see in the mid-latitudes. So some of these numbers that we say here for New Zealand may be some of the greatest precip rates that we see. They might be peered by a few on the west coast of sort of Canada up there, but yeah, pretty extreme precip, and then you dry out very quickly as you go to the east. Again, up in the North Island, where the mountains are, is where they get their precip. Sweet. But that also turns into snow. And so up in the Southern Alps here, this is about 2,000 metres above sea level. This is the end of season snowpack on a glacier. This is our snow pit dug down to the ice surface, and that's 4 metres of snow that fell in a single season, which is a decent amount. And we care about that snow and ice. And so when we look at our river flows, about 17% of our annual river flow comes from seasonal snow melt. And so the timing of that melt is really important for things like irrigation and power generation, especially on this eastern side of the country that you saw gets very little rain. This particular attention to focus on the Waitaki River here. 17% of the runoff, the annual mean runoff of that river comes from seasonal snow melt. And you can track that back into these big lakes right to the east of our highest mountains here. So the Waitaki has 17% of its stream flow from snow melt. But what's even more important is that the Waitaki River provides 20% of the nation's power. And so you can start to think that any changes in that stream flow in that river system could be pretty important. So 60% of our country's national grid comes from hydropower, and the Waitaki River is a third of that alone. And when you look at this power station system, we have these big lakes, these big old glacial lakes dug into these valleys. And every end of the lake and a few canals down the way have power stations. And so we really care about how much snow is falling into the mountain and coming out of that mountain. But then also the snow and ice has big tourism value. Skiing and glacial tourism, here's me and some friends admiring a glacier. And there's plenty of money in those industries, and so we do care about where our ice and our snow is hanging about. And there are businesses that rely on this. Here's me dodging some helicopter blades up in a glacier. There's reason to study these. And so we have this program, the Brewster Mass Balance Glacier Program, which is the longest running observation program in New Zealand for a glacier system to study the drivers of mass gain and mass loss. There's been extensive weather station observations. So this station here has been at the terminals for this glacier for about 15, almost 20 years now. And then throughout the period of the observation program, there's been stations embedded within the glacier doing full energy radiative transfer, and we've done eddy covariance flux towers as well. And then also seasonally, end of summer, end of winter, seeing how much snow falls, and then ablation stakes, looking at how much mass is lost off that glacier. So it's an extensive program which requires a lot of field work. But it's to answer these questions of, do we know what provides us snow and mass loss in these mountains? And so we get cool data sets. And so this is a surface height change, and so we lose height in the summertime, we gain height in the winter, and over these 2 years, 2011 to 2012, our winter time does not match our summertime, and that sort of matches our story that we're losing mass in our alpine glaciers. And some of the field work allows us to do full spatial maps of where we're gaining and losing that mass. But the question we have is, what drives extreme melt events? And this is sort of where my work kicks off. That do we know the sort of weather events that can cause mass gain and mass loss? So on the left is just it's a composite map of the top 10 largest melt events looking at the vapor flux. So you can see here, if you take an average of the top 10 events, you just get a northwest flux coming over. And then an earlier paper, Gillett and Nicholas Cullen, Sarah Gillett, plotting ablation per day, so our melt rate versus our energy balance components. So you can see here with our low melt rate, our radial fluxes are pretty important. But as we increase our melt rate, the importance of those radial fluxes reduce, and definitely our latent heat starts to dominate the flux available for melt. And then our rain heat flux also pops in there as well. So moist, rainy days is really important for losing lots of mass on our glaciers. And then some more recent work, Kieran Little got into that a bit more, looking at just maps of extreme melt events, and these are two of the most extreme melt events we saw on the glacier, again plotted with the moisture flux, and it just comes through this big northwest plume. It's fundamentally important to glacial mass loss. But Kieran also looked at the mass gain events too, so our snowfall, and a similar pattern appears. These are two of the heaviest snowfall days. So it starts to look like some of the same weather systems might be responsible for both providing us mass gain and mass loss. Although if you flick between these, you can see the magnitude, which goes from blue to red, is certainly reduced, but it's still that northwest plume, definitely more northerly there, but comes through for both events. So this is the question that really came through in my master's. We want to study the nature of these moist advection events, their seasonality, their trends. What sort of synoptic conditions cause these? Can we detect them? Can we forecast them? And how might they change into the future? And if you look closely at these, they look very similar to what we see on the west coast of the US. And so very quickly you can make this parallel that these moist advection events we see in New Zealand match up really well to these atmospheric rivers that people like Marty Rolfe and Ben Guan really started to address on the west coast of the US. And so we can use some of the research they did there, use their detection algorithms, and see, are these the same sort of events, and can we answer a few of these questions about the seasonality and nature of these extreme moist advections in New Zealand. And there was one other paper, Daniel Kingston, who was 2 offices down from us in Otago, who did the same similar study for lake inflow events, and he also found these moist plumes across the country cause enhanced lake inflow, which makes a lot of sense, that moisture equals rainfall. And so if we can identify these things, we can build climatologies and examine their meteorological forcing. And here's an example of one of New Zealand's most damaging ARs. It's this big plume of moisture that comes across the country, perpendicular to the mountains, and dumps rain on the western side of the mountains. And then we can start to calculate statistics of their impacts, a few of those ideas. And here's just a quick, brief overview. For those of you who haven't come across atmospheric river detection before, or AR detection, it's this idea that if it looks like a big plume of moisture, then it's an AR, really. And we have these criteria. If it's extreme, if it's coherent, if it's poleward, if it's consistent, and if it's large. And there's just a few of the more subtle criteria that puts in there. So if the IVT magnitude meets the 85th percentile for that pixel, if the flow is together, if it's flowing poleward rather than equatorward, it cannot straddle the equator. The flow must be along the primary axis of the object that gets detected. And then it must be long. And so most of the moisture fluxes in the mid-latitudes come across, they all meet these criteria. And just an example, here's a map of all moisture that exceeds this threshold of 250 kilograms per meters per second. You can see the tropics pop off there as a region of enhanced moisture flux. But once you apply that criteria, in this case that guano-molyzer detection, we remove the tropics and we only end up with these mid-latitude plumes, which is sort of what we want to study. And so we can make quite a good argument that applying these detection algorithms get us to the events that we want. If we want to study moist advection, AR detection algorithms take us there. We can do good work. Sweet. So we can get a bit of the science here. Sort of the mean New Zealand atmospheric river, the flow's nor'wester. And so we're starting to meet a few of those questions from our so nice. AR occurrence is a bit more interesting, that ARs are more frequent to the south of New Zealand, to the north, even though moisture flux tends to be higher in the north. And so the idea is that westerly winds might be important for that moisture flux rather than the gradient in moisture itself. And here's a few more examples of, sort of the different flavors of ARs we can get coming across New Zealand and what they might look like. And there's one extra thing to introduce before we move on to a few of the other results, is that again, on the West Coast, Marty Rolfe and his team at Scripps introduced this AR ranking scale that we can rate the potential damage or intensity of this event based on the magnitude of the moisture flux and how long the moisture flux exceeds a certain value, in this case that 250 range. And here's just an example of one grid cell time series. We're coming along 2018, and then at some point the moisture flux exceeds 250 plus as an AR, and then we see how high it reaches. In this case, it exceeded 750, and it lasted for over 24 hours. So in this case, that would be plus as an AR3. which their descriptions are, it's a balance between beneficial and hazardous, and these come from observations from the US West Coast. And one of the questions is, do these observations also work in other places in the world? Or is this scale purely for the US West Coast, or is it pretty universal? Can we say that an AR5 primarily hazardous will be primarily hazardous anywhere in the world? Which is an interesting idea. Does this apply elsewhere? And just as another look at that, of how it sort of works, is that this isn't per object, this is per grid cell, and so it's how a single grid cell experiences the passage of this moisture flux. So say this block of data is a single object passing through each time step, and if you look up from each grid cell as that passes, you can say, well, in this grid cell it only lasted for 24 hours, but it didn't exceed 250, but in the center of the country, we definitely made it to an AR5. And so it is grid cell specific, these results. And now into the seasonality. Up in the north of the country, this is the big result that comes out of this work. In the north of the country, we don't see much of a seasonal cycle, especially compared to down south. And so down south, from this work, we really define the summertime AR peak season. If you look at the colors, so AR1 is the blue, going up through to red, as being beneficial through to hazardous. In the summertime down south, in Dunedin and Doubtful Sound, which are two locations down south, we get more damaging events in the summertime. And then the total number of events really drops down in the winter, which matches the seasonal cycle of precipitable moisture. It's high in the summertime, as we'd expect, and dips in the winter. But up in the North Island, which is much closer to the tropics, we see much more persistent occurrence of all classes. So we can get AR5's event all the way through in the winter time, up in these two very north locations, up in the top of the country. So already we're seeing differences across the country, which will be interesting to explore, sort of where that comes from, what drives the seasonality. We'll come back to that.
Could I ask about Australia and the season? If you peak in the going into the summertime, then I might think, well, upstream there's Australia, that might inhibit the process, it's sort of dry.
Yeah.
But maybe it's the overall sea surface temperatures and moisture source. I guess my question is, where's the moisture source? Because you have a local curved path across the Tasman Sea, which doesn't have that great of a fetch.
Yeah.
Is that where all the moisture is coming from, or is it farther upstream?
We get into that.
Okay.
Yeah, later on we'll touch on that when we get into the genesis of these events. But it's definitely a really important point. Australia is very important for New Zealand ARs, and that's one big difference between the US West Coast and New Zealand. Is you have this big landmass there that not causes problems, but it makes it a different flavour of moisture source. But New Zealand is also unique, is that we can get fluxes from any direction. It's sort of one of the only locations in the mid-latitudes where you can have a very thin strip of land and moisture flux can hit it from every location. And so that's part of what we can explore here too, is that we can get varying synoptic conditions that cause ARs to make landfall in different parts of the country, and they might cause similar damage. Of course, West Coast events dominate all landfalling. It's about 90% of all landfalls make landfall on the West Coast, and we get this pressure dipole that we'd expect. The geostrophic wind bringing that moisture across, maybe from the Tasman Sea, or maybe from a different location, but blown across New Zealand. And then to get it landfalling on the north coast, get that, and then it has to wrap around to make landfall on the east coast. And when we plot the moisture flux anomalies, that's certainly what we see, is that this enhanced nor'wester, and then the northerly, and then this easterly. This is moisture anomaly, standardized anomaly of the moisture flux. Sweet. And so we get this idea of what is the average New Zealand AR. Cycling to the southwest, a cold front extending to the northwest across the Tasman Sea, this northwesterly geostrophic flow across the country, and enhanced moisture over eastern Australia. So sort of this plume here is where we see the moisture. One point that comes up in a lot of these talks that I've given in the last few years is often from operational meteorologists who say we already detect cold fronts and we already have models that predict precipitation. Would this also appear if you just detected moist cold fronts in the country? And the answer is probably yes. That most ARs that hit New Zealand, we just see as a cold front that has this tongue of moisture. And certainly we can get cold fronts that don't have that tongue of moisture. But yeah, it's an important point to cover that often the argument is, yes, it will be the same thing, that if you detect a cold front that has a moist plume, that is probably the same thing that we're detecting here with that enhanced moisture flux. So coming back to this idea of seasonality, can we describe that seasonality in a bit more detail? And this builds off some of the work from likes of Kevin Trenberth and Mark Sinclair, looking at southern hemisphere cyclone densities and tracks and things. I know this is some work being done in the department at the moment, talking about a southern hemisphere polar wintertime jet. Does it even exist? This is still up for discussion, and we're still building this idea of why don't we get, or why we get sustained occurrence in the north of the country. So in the summertime, it's fairly easy to explain. Sort of we get this polar jet, and we get this max cyclone density between 50 and 60 south. If we position our cyclone there, and we draw our cold front up, we can easily get our mean conditions. But then in the winter time, when the seasonality or the occurrence drops down a lot in the South Island, but it stays frequent in the North Island, the idea is that the split jet, that this directed polar jet drops too far south to pick up the moisture. That it's too far south from our tropical plume, our tropical reservoir, to tap that moisture, to pull it down our cold fronts. Because we still get plenty of cyclones passing the South Island in the wintertime. But up north, we do get this max cyclone density associated with that subtropical jet, and the idea is that that can maintain these enhanced poleward fluxes in the further north of the country. But it's still a working model, and we're still doing a bit of work here to really characterize the southern hemisphere sort of storm seasonality, which hasn't really been touched on before. But there is a few complicating things, is that New Zealand does get tropical cyclones. We get about 3 each year passing down into the country. Many of them undergoing extratropical transitioning. And when we compare them to our AR detection, about 94% of them have this associated extreme moisture flux as part of their life cycle. So here's a good example, tropical cyclone Oma back in 2019, spinning off here on the east coast of Australia, has this big plume of moisture carried down with it that then joins up with this extratropical cyclone, and you get this sort of paired system that's blowing moisture across the country, and they get wrapped up further south, which is certainly a really interesting case. And here's another one, Gavin. This was back in 1997. Again, you can see the tropical cyclone moving south into the country, bringing this plume of moisture down with it, which again was detected as an AR object with that red outline. But then here's an example of one that wasn't. Cyclone Vola in 1988. Certainly was very moist, but the advection of moisture wasn't high enough to be detected as an AR. And so cyclones, tropical cyclones may cause some problems here. It's certainly an interesting point to add into the world of atmospheric rivers around the world, is that we get these very strange cases in New Zealand of TCs that bring down moisture that then becomes this whole mix of moisture in the mid-latitudes. It's certainly interesting. Get into a few of the impacts. So in those previous plots with the snow and ice, we were saying that with snow and ice, moist nor'westers appear to cause mass loss. And the same sort of ideas come across when we look at the precip. This is about 200 stations, weather stations across the country, rain gauges, with at least 20 years of data. And if you look at the total percentage amount of precip, on the western side of the Alps, those purple colours there, we get about up to 70% of our mean annual precipitation on the western side of the Alps comes from these detected moist plumes. Definitely drops off to the east. And so on the east of those sides, we get under 30% of the rain that falls all the way down the eastern coast comes from other sources, which is an interesting question in itself, what might cause the precip on these eastern sides. When you look at the extreme precip, so you look at the 98th percentile of 6-hourly precipitation for all these rain gauges, those numbers really jump up. And there's some locations here on the western side, or right within the mountains, that it jumps up to 95, almost 100% of these extreme rainfall events come from these detected ARs. And again, we jump to the eastern side, those extreme rains are coming from something else, which starts to spike a few of our other research questions. What causes East Coast precip if it's not these intense plumes of moisture? There's other things going on. But mountains are important. And so coming back to the scale, does it work in New Zealand? And so these 3 locations here are all bunched up on the western side of the mountains. You can see here Hokitika, Crop River, and Ivory Glacier, clearly a weather station and a glacier, but they're all deep within the mountains on the eastern side, and they all follow that trend. That as we increase AR rank, as the moisture flux and the duration increases, our 3-day precipitation values also increase, which aligns with what we see on the US West Coast. But just take a note that here at Crop River, some of our 3-day precipitation amounts get over a meter. That's some pretty intense precipitation rates to get a meter of water over 3 days. But as we jump around to other locations in the country, Doubtful Sound down here in the bottom, we do get an increase. But then somewhere like Dunedin, which is on the eastern side of the mountains, we don't see that. But then up north, Auckland and Kaitaia, right up here, we see that increase coming again. And so there's this idea that this rank might work well in New Zealand. It certainly works well on the west coast. But in somewhere like Dunedin, there's other controls of our precipitation going on there. And then to finally answer our question, is it important for the snow and ice? Yeah, it is. About 50% of the total melt occurs during these AR days, which accounts for about 10% of the time steps. And so characterizing what might change this number, will this become 11% or will it become more intense? Will we get more melt, since a large portion of the melt is governed by these things. And then 71% of those extreme melt days come from these extreme moisture fluxes. Switching over to the snowfall, we see similar numbers. About 50% of our total snow falls during these moist nor'westers coming across the country. And then 80% of the extreme snowfall days occurs during these events. And there is strong agreement between melt days and heavy precip. The days that we get extreme melt, we get flooding in the rivers.
Is there a change somewhere, Hamish, on the calendar about what used to be snow days are now melt days?
Yeah.
And how has that moved?
That's a really good question. And we certainly see the intensity drop. So the moisture fluxes that bring snow are much lower than the moisture fluxes that cause extreme
Because you're
melt.
crowding them into the depths of the winter a little bit more than you used to, right?
And they are colder, and there's plenty of work. Some work has been done, plenty more to be done about that, of cold ARs bring snow, whereas warm ones bring melt. But you do see that seasonal switch. And that'll be an interesting thing to study in the future. Does that change, or have we seen that change? Sweet. And then let's just jump into the impacts before we move on from New Zealand. Is that this question, is AR5 damaging? And so the last 7 AR5s in the last 40 years, 5 of them have destroyed bridges on at least one state highway on the western side of the country. And on the west coast of New Zealand, it's fairly remote. There's 30,000 people who live in this whole circle here, which is less than the student population of Wisconsin. But there's only a few mountain passes that take you over into this region here. So as soon as you lose one of these bridges across one of these wide rivers, you isolate an entire community of people. And so these things are problematic. That protecting ARs on the west coast of New Zealand does have very real impacts on people's livelihoods. And from the insurance claim records, up to $4 million of damages gets recorded for single flood events that come through on the west coast. But compared to the east coast, that's about 10 times smaller, and that's all because of risk. Where are the people? Where's that industry? Where's that power generation in our cities? They all live on the eastern side of our country. And so when you do get those storms coming through that cause melt, that cause flooding on the east coast, that's when some of the extreme damages really come through. And so there's almost a question here, do we study the precip where it's heaviest and most interesting, or do we study the precip where the potential for risk is highest? And that's almost pushing us into what do we study in the future, sort of aligning our future research questions here. And certainly there's a few of our power generation stations, they have to let out water, they have to prepare for these events. And then up north, up here in Gisborne, there's a mountain range here, and if you ever get a moisture flux pointed towards that mountain range, those rivers start washing out. You can see here, this road is precariously hanging on to the side of this slope here. So East Coast landfalling events may be more important to study, even though sort of geophysically they might not be as interesting, but in terms of the potential for damage, they are much more important. And so just some quick work that I've done here on East Coast landfalls. I went through and plotted the top 10 precipitation rates for every weather station on the east coast of New Zealand. And I plotted the geopotential height anomaly, the moisture and the moisture flux. You can see little arrows here on this graph. And then the AR outlines, if there was an AR detected, what does it look like? And so this is really a question, what causes an east coast moisture flux? And it's these wrapped up cyclones, almost, when I scroll through these, they do appear to be almost, or also occluded. These mature cyclones that pull that moisture all the way around to then be easterly into the country, and those are the damaging events. Down here in Dunedin, we also see that, to cause that moisture to wrap all the way around, then make landfall here, and also here. So this is the third and fourth most intense precip days in the last 40 years. They are 2 different days. They look very similar, but they both caused quite intense precip rates. Again, to wrap up all the way around, then make landfall there. And here's Christchurch, in the centre of the South Island. Again, wrapping that moisture all the way around, then make landfall. Not necessarily detected as an AR, but this, fully occluded cyclone, you could almost say. And there is plenty of future research to be done here on the role of occlusion on East Coast floods in New Zealand. And I think there's certainly a very cool proposal to be written on that. Rudra.
So I have a quick question. I'm curious as to, did any of your tropical cyclones that you saw caused an AR event on the north of New Zealand?
Yes, if you go back to those. Here. So the green outline is the detected AR.
Yeah.
So that's the moisture flux. And like, you can certainly argue, is this moisture flux here associated with the tropical cyclone, or is it completely detached? And it's just, they both have high moisture, and so it gets grouped as the same system. Maybe this is entirely associated with the extratropical cyclone down here, and it's just the cold front stretching back through here. But at some point it connects, and so it gets detected as one whole object. And then here again, you can see the moisture flux in the cyclone, and then it also gets drawn out. And so they're happening together. I don't think you can separate it. But yeah, certainly. And some of the most extreme weather in the north of the country do come from tropical cyclones. They are damaging.
That was my question. Like, probably the tropical cyclone is like pushing it more towards the north.
Yeah.
Okay.
But yeah, it's just some interesting work that occlusion could be really important. And if I find some kind of mid-latitude cyclone life cycle algorithm to then find the occlusion events, I'm sure most of our east coast floods will pop out with those easterly moisture fluxes. Yeah, let's quickly just go over this. Hey, Potion. Do you want to find mature cyclones from here?
We do, we know how to do it now.
And just one touch here, I won't go too long, because this is the most recent work I've been doing with Ben Pole on MJO interactions. And so, just scrolling through here, this is phase 1, so MJO is the shifting regional tropical convection that shifts across the tropics. And so as I scroll through this, phase 2, so the vectors of the moisture flux, the colours are IWV anomalies, so that's our precipitable water, and then our geopotential height anomalies at 500. You can see here, phase 3, phase 4, that regional convection shifts across, 6, 7, 8. And you can see, just by watching this scroll through from phase 1, 2, 3, we get moist New Zealand in the middle there. And this is not something that people really have discussed before, of what role does MJO have on New Zealand. And it does appear that as we go from phase 1, it appears to be dry, we have these are anomaly vectors. So they're anomalously equator, so we have reduced poleward moisture flux in phase 1. And as we come through into the middle phases, Indonesia gets wet, and we get this plume of moisture coming down, associated with this low pressure over South Australia, and then this high pressure dominating over here. And this is an interesting one, that we get this low and high dipole and this enhanced moisture flux anomaly through there. And just looking at a few of the life cycle characteristics, and so these are some of the numbers we can get out from tracking ARs, is that we can get things like travel speed, the max IVT, the max precip, and we do see a modulation going on. So our travel speed, during phase 1 and phase 8, our ARs tend to travel faster, which is an interesting idea that during this phase, any moisture flux that does pass through New Zealand passes through quickly, and we could almost associate that with this pressure anomaly, this sort of zonal flow that increases the speed of these moisture fluxes coming through. And as we jump through into our phase 5 and 6, the zonal velocity, the travel speed of these moisture fluxes really reduces. And that could be associated with this sort of directed back into the flow. We're sort of digging in with our moisture fluxes so they don't get pushed too fast. And again, as we expect, those middle phases have high moisture flux, and those outer phases at phase 1, so deep convection sort of in the central Indian Ocean, and phase 8, when that convection moves off into the Pacific, we get these dry anomalies well over the rest of the country. And we're just starting this work here, and there's plenty more to be done. Some ideas of teleconnections. Does convection back here generate a wave that comes through? This is just 10-day composites following each phase. So nothing complicated, but we do want to get more complicated here and do a few other studies.
So one thing that's kind of cool that comes out to me is, but it's not on the diagram, but it might be worth investigating, what is superimposed upon this, the smaller scale, both in space and time, of the eddies that come along with these various composites. Because maybe the phase 5 or 6, where you get that strong northeasterly flow over the country, that might be a time when you get a lot of occluded cyclones driving by at 40 degrees south or something like that, and so and they've got the available moisture from another cause.
Yeah.
That's really cool.
And certainly phase 6 is when you have convection up here.
Yeah.
So you have that moisture there, ready to be pulled down.
And you have an enhanced cyclogenesis frequency at the same time.
Yeah.
At 40 degrees south.
It'd be really interesting to look into that.
It looks like the radiation of the planetary wave train is robust from the MJO and across the Pacific to North America.
Oh,
Yeah,
yeah.
it sure
But here
does.
you also see that wave coming out here.
Yeah.
So deep convection here, you start to get this wave pattern coming across, and then it shifts, and it shifts again, and then it starts to tilt the other way.
So is there MJO signal and sea level pressure over Antarctica?
It's a really good question. This here almost looks like a Munson sea low that starts to pop out, but that'll be hard to argue. Sweet. Let's move on to more life cycles. And so we're jumping back into our northern hemisphere. Maybe we're a bit more comfortable up here. And this idea of tracking ARs back to their genesis and seeing if that can tell us anything about what they might be like when they make landfall. And so just to talk about some of the data we use here. So this is when we jump into the insurance claim data. And a lot of this is attributed to the work from Thomas Corringham. He did his PhD at Scripps. He's a geoeconomist, is his title. And so for his PhD, he went back through the FEMA's NFIP program, so the National Flood Insurance Program, which is a really good record of flood insurance claims in the US over the last at least 40 years. I think it goes back to 1960 maybe. And so through his work, he comes up with this workflow. So you adjust all the values for current day US dollars. And the NWS also has a record of economic impacts. And so as extreme floods come through, the NWS do go out and ask councils and local governments how much costly was this flood. And it comes up with this very simple multiplication that recorded flood insurance claims, times it by 30, and you get to the total economic impact. Importantly is that the recorded flood insurance is only from residential insurance. But through his PhD, and there's a really good thesis, if you're interested, to go read on that relationship, that if you times it by 30, the housing insurance comes out to total. But importantly, the NFIP is really high spatial resolution, so they get down to sub-county level data. And so this is at the state level, but if you jump down to the counties, you can do some really interesting impacts of individual floods coming through. But there's lots of things to consider. Potential for damage is one of them. Where do people live? Where's the expensive properties? Where's the old properties? Do people live in floodplains? Economic engineering developments in the future, are we going to become more resistant to damage? And yeah, where our population centers are. And so this is one of the first figures from my paper from last year of how impactful are ARs on the US West Coast for their flooding damage. And in California, 96% of all flood insurance claims come from ARs. Sort of all economic damage that gets recorded in the California comes from ARs. Unfortunately, this is just flood insurance. If you look at fires, these numbers drop right down. Fires cause way more damage on the US West Coast than floods. And so this is almost taking one step down, and we're just looking at flood insurance damage. But we're now detecting what causes all that damage. we get that number. 88% of all flood insurance claims on the US West Coast comes from ARs. And we apply that scaling. Are AR5s primarily hazardous? Yeah, they are. This is $1 billion on average is from an AR5. You never get an AR5, extreme moisture flux and prolonged moisture flux. You never get no damages. You always get this range. And keep in mind, this is a exponential scale. So as we jump down through our classes, AR4 scores 40 million, AR3 scores 3 million on average. We jump down through our scales. And so certainly this scale that was proposed seems to be holding up pretty well. And one important thing, this is quite a subtle point, and it's not really a nice figure, we have some pie charts. It just shows the proportion of damage that comes from each landfall. And so the purple is landfalling events in Baja, California that come through here. And so here in Arizona and New Mexico, we have majority, so over 50% of the flood insurance claims come from ARs that come up and behind. So they're not coming this way, the storms have to come this way predominantly towards the damage there, which is really interesting. And even up in, is that Utah? Yeah. 33% of the damage comes from storms at landfall in Baja. So there's this idea that does the storm sneak in behind the Sierra Nevada to cause these flooding damages in the interior of the West Coast. Whereas somewhere like Washington, 94% of damage comes from events that make landfall in Washington. The reviewers were very questionable of this figure, and there's certainly a lot of assumptions and work to be done on where does the damage come from. But just as a first look, based on these broad West Coast regions of the importance of the Sierra Nevadas and maybe sneaking in behind those mountains. So just one quick note on genesis, is that when we talk about genesis, we're talking about a region of moisture flux that has increased in magnitude. We've gone from no moisture flux to a point of having a moisture flux. And so we're saying, at what point does this become a synoptic scale feature capable of producing precipitation? And it's almost always associated with a developing mid-latitude cyclone. We get these numbers that 80% of genesis occurs in sequence, sort of co-current with a developing mid-latitude cyclone. And yeah, it's often that pre-cold frontal lower level jet. And here's just an example of what a life cycle might look like. Genesis in the Pacific, a third of the life cycle through, we're almost making landfall. And 2/3 of the way through, we've made landfall, and then termination occurs, both in these cases after the moisture flux has made landfall, and it rains out its moisture, it loses its moisture, and it's no longer classed as a feature capable of producing precip. And so this is a figure I do want to spend some time on. And it's the final result of all this work here, that damaging ARs tend to come from further across the Pacific for every landfall location. So just to talk through this, the colors is the percentile of AR damage, and the dot is the median genesis centroid. And so if you look at all ARs, the white dot is where the median centroid is. So you can imagine the shape of the moisture flux around this dot here. And as you increase that damage percentile, it almost exclusively moves westward. So damaging floods tend to come from further west.
And not further south.
Not further south.
Yeah. Interesting.
There's a wee southward shift, but it's further west. It's west across the Pacific. And when you look at the moisture flux associated with that, so again, here's our longitude, it should sort of match up one for one, the figure above. As you move further westward, your moisture flux increases. Like that is quite a compelling relationship we see there. And there's a few ideas. Do ARs that travel further, do they have the potential to pick up more moisture? Do they look substantially different to normal ones? Is there something fundamentally different to storms that come from here for Oregon versus storms that come from here? And it's some interesting questions to be done there.
You mentioned occlusions, that the older the storm, the greater the flux.
Yeah. So the idea of scavenging moisture comes along as well. And we can get into a few of the spatial statistics here. So these are all just medians, but if we look at the grid cell based, here's all ARs for our Washington, Oregon, California, and Baja, and then the 75th percentile damaging. And you can see as we go from yellow into blue, we get increased frequency of occurrence, so increased genesis frequency in this high percentile, and then here is the statistical difference of those grid cells. And you can see these regions start to appear. That damaging ARs tend to come from these regions much further across the Pacific than what might typically be called the normal ARs for those regions. Certainly for Oregon and Washington. When we get further north, those ARs come from further west, as we see from here. So we get those regions popping off. These West Pacific ARs tend to bring the damage.
What about 300 millibar jet in all these
Aha.
different composites? Outstanding.
Now that you mention that, we can look at the synoptic features of these events. So on the left is all AR genesis for these 4 locations, what that looks like, with this 300 jet being in the yellow colours on the graph here. The geopotential height being the blue and the red, and then the moisture flux anomaly is on there as well. And one of the ideas that comes through is that damaging ARs tend to be more zonal. We get a zonally extended jet, especially for Oregon and Washington. The following one shows a bit more. This is only West Pacific ARs. So if we say we only want to look at West Pacific because we know they cause damage, we get this zonally extended jet across the Pacific with these multiple sort of cyclonic centers coming out of there. We get a few of these interesting conclusions that can be made. One of the findings is that when you look at only the West Pacific features, you also have high moisture flux almost making landfall at the same time. And Meredith Fish, who was a PhD student at Scripps a few years ago, came with the idea of AR families, that often you get multiple ARs coming through. So you go through periods of time where you're quite relaxed, and then other periods of time where your moisture fluxes follow very quickly behind each other. And it is often associated, 50%, I think, of damaging West Pacific ARs are an AR family. And so if we're detecting a genesis here, there's also intense moisture occurring in the East Pacific as well. Which is an interesting idea that when we get West Pacific genesis, we also have East, which may increase the potential for it to have a higher moisture flux. And this work isn't new. There's been work done on this before. Soderman and Stoll looked at moisture scavenging of multiple events coming through that can pick up moisture from previous events. And so maybe having the events come from the West Pacific, they have the potential to then pick up moisture in the East Pacific that have been left behind by other poleward advections. So yeah, the scavenging of previous moisture fluxes, and that's why we might see such a domination, like such a compelling change to westward as we get more damage. And again, we'll skip over that. But this isn't new either. This is from a report from NOAA about that 2005 event, and they discuss it as this unusually rich subtropical moisture plume originating near the Philippines of the West Pacific. So that was back 15 years ago. And they drew this picture. They drew this wee animation of the zonally extended jet, allowing this plume of moisture to extend across the whole Pacific. And the difference is we can now detect what these are. We're detecting this plume here and saying, can we see that that comes further west? And it all starts to match up. These previous reports from NOAA and these sort of case study analysis match some of the statistics that are coming out. And one last point in the last 5 minutes before we finish up. Do we see the same results in New Zealand? And kind of, but going back to Matt's idea, Australia is important. And so when you plot where genesis is for New Zealand, it is hampered by the presence of a landmass here. You still have genesis extending back, but the longitudinal extent upstream of genesis for New Zealand is much smaller than the extent you get for the US. But interestingly, the outflow, where termination occurs, goes right across the Pacific. It gets caught up in that westerly jet, those westerly winds, and we even get landfalling events in Antarctica that have passed through New Zealand. So there could be an interesting study there. Does flooding in New Zealand, is that associated with the same storm that might cause rain in Antarctica? It's an interesting possibility, and this sort of raises that point that genesis here passes over our country, and goes across that whole coastline. And when we look at that frequency difference between that same idea of the most damaging versus all of them, we get a very different picture. We don't get a westward shift, we get a sort of geographic spread outwards. So for the North Island, we get this region in the North Tasman Sea, which is known to be hot and warm, and there's plenty of extreme marine heat waves going on there. That pops off as this region that's important, the genesis region for somewhere out like Auckland. As we come further southward, Taranaki, which is this purple diamond here, sort of in the middle of the Tasman Sea. Hokitika sort of extends across Australia, and this idea that there could be moisture that comes from behind Australia that gets picked up in a cyclone over Australia that then makes landfall in New Zealand is a potential cause for that. And then interestingly, in Fiordland, we get this streak south of Australia. And so the extreme events don't have to be tropical plumes from the North Tasman. It could be south of Australia and the bight here, even coming from the Indian Ocean, coming under, sweeping through and then causing rain in Fiordland, which is certainly interesting. And one last point here, if we look at the synoptic conditions for these events, so similar to before, but now we're looking at the day of genesis and a lag correlation, so looking at 2 days before genesis and 5 days before genesis, what does it look like? And this is for Auckland, so in the north of the country, and then we do 2 days. Typically, landfall occurs about 5 days after genesis, and so you can see an intensification of our moisture flux and our pressure anomalies as we go after. But the one point I want to pull out here is in this extreme precip in Auckland, over these 10 days, we get this pressure anomaly just off the coast of Antarctica, which you might descriptively say looks like the Munson Sea low. But if you start to draw a wave pattern here, you almost get this planetary scale wave coming across with this embedded short wave causing this wee peak of moisture transport here, but you get this interesting pattern coming through. And if you plot an animation of that, sort of a schematic, you get this pattern. For North Island, you have this big planetary scale wave with this embedded short wave bringing that moisture. And then South Island is a bit more complicated, but it just shows that the moisture comes from different regions for different parts of the country. And yeah, this is huge. This is 90 east to 90 west. That's half a hemisphere, half a longitude band, a latitude band. So yeah, a wave number 1 or 2, and it'd be really interesting to see if I can sort of come up to a way to diagnose that. Is this coming from the mountains of South America, from Patagonia? Has it been initiated from something upstream? But you can imagine this coming through as a big wave across the entire southern hemisphere. Sweet. That brings us to the end. Moisture flux is important. Direction is really important. That's one of the things that come out from this work. Not just magnitude and duration, but direction, particularly with regard where the mountains is. Peering our socioeconomic data can help direct our research, and that sort of sparks for some of our new research questions of those east coast landfall events of cyclone occlusion, rather than studying the interesting heavy precipices on the west coast. And yeah, some of those North America findings that as it travel further tend to be more impactful, and then in the southern hemisphere, these planetary waves and occlusions are really important, and I'd love to develop a methodology to study some of those events further. Can we detect those waves? Can we detect what initiates these synoptic patterns? Sweet, thank you. Any questions?
Yeah, great talk, Hamish. Thanks a lot. Really interesting. I'm thinking about the western United States ones where you go Washington, Oregon, California. They have further distances to travel.
Yep.
And it does look like the jet, the zonal extent of the jet matters too. And so I'm wondering if part of the story is that when you have a retracted jet, maybe it gets back to 180 degrees longitude, and that's where the development of the cyclone that delivers the AR to Washington State starts to go. And then, of course, it's going to head poleward, all cyclones do.
Yep. And
it has a longer distance to travel. It can develop more on its own once it gets kind of off of the jet. And so that might be the reason why you get the moisture plume that's substantial enough to be, an AR by the time it gets to Washington State. And so I'm wondering if the intensity of the sea level pressure disturbances is also larger the higher latitude you go. So the Washington storms are stronger than the Oregon ones that are stronger than the California ones because they may get to develop at a later stage. And if you're at 35 degrees north off the coast of California and you develop a cyclone, as soon as you start to advect water vapor from the southwest to the northeast, that's a larger pool of water vapor than it is at 50 degrees north.
Yeah.
So I wonder if that's part of it. Fetch is working in favor of an intense IVT, but latitude's working against it, so the combination is the only thing that makes them all about the same.
Yeah. Interesting. Evan?
another question about the same topic. So you're using the 75th percentile, like economic damage to find these storms, and you also talked about the families of ARs, and I guess I have two questions. The first one is, in that economic damage, how well can you separate multiple AR events if there's damage happening from like multiple ARs that hit within days of each other? Like how could you separate that?
So the tracking algorithm does a really good job of detecting each individual disturbance, and so they all get individual IDs. And so you can number these events that come through and see this event that made landfall. It's a 6-hourly data set as well, and so you can split it up 6-hourly.
So I trust the tracking algorithm. What I'm saying is, if you have multiple events that are causing economic damage right after one another, I would imagine that A, it might be hard to separate which storm the damage comes from, and B, if one storm comes and then another storm comes right away, it might cause more damage than it would have otherwise.
And that is this idea of AR families, that when we're detecting West Pacific ARs, that we already have a strong moisture flux. And so these damaging ones in particular, you already have moisture being dumped on the west coast, and so you have antecedent conditions that by the time this storm comes through, it doesn't have to be too high of a magnitude to then cause an extreme precip. So that tracking westward may just be a function of you have other events upstream that cause conditions suitable for extreme damage.
Can you tell, because you have those classifications and you have a bunch of outliers like in your different AR scales, can you tell if more ARs that seem like they shouldn't be damaging based on that scale are occurring in this sort of scenario because they're following maybe a trainer family?
That would be really interesting. And all we did was just get those statistics of Meredith has this data set of what is an AR family, and you can just match that with these events, and 50% of West Coast events are part of an AR family. And it's more of a function that if you do get the zonal extension of the jet, you will get multiple things coming through.
Right.
That is, it just has to happen. And so you'll get damage. So maybe it's more a discussion that a zonally extended jet is what causes flooding on the West Coast rather than the individual ARs. That could be the final conclusion to make there.
And then the time scale of the zonal extension. They don't last forever. They do retract. And so they have a characteristic time scale. And it might be that it matches perfectly with n number of synoptic events that can propagate along the jet. So you can really kind of start to see that, I guess.
Yeah, this wave guy that's passing straight.
Yeah, there might be 3 events that'll make it in the length, in the time scale, the lifetime of an extended jet.
Yeah.
That's very intriguing
Is that just the time scale of the planetary wave?
Oh, I don't think it's quite that simple, but we don't know yet. Why does it take so, it's about a 10 or a 12-day time scale. When it gets extended, it stays that way. On average, about 10 days.
And if you look at this, that 10 days matches really well if you look at from December 20th through to the 30th.
Yeah,
so
that's
it's 10
one
days
example.
of
That's
just
right.
full zonal infection. Posh, you had a question?
Yeah, did you happen to look at the seasonality of the westward shift as well as the cyclone families?
Yes, and I don't know if I put it in here, but you do get an oscillation. So as you move out of the storm season, you get like a cycle going on. I can show you later, but there is a seasonality to where the storms come from.
Yeah, I'd be interested in seeing that because in the data that I looked at, which is consequently right after this year. So in the northern hemisphere winters, you start to see in the latter half of them, you start to see the cyclone families starting to pop up, and that's an extended jet. So what I'm looking at also matches what you're looking at. So I'd be interested to see how the seasonality works and how it compares with the southern hemisphere as well.
Yeah, I did make a seasonality plot.
In terms of cyclones,
Yeah.
northern and southern hemisphere.
That was one of the reviewer comments. Please give us a seasonality.
Okay.
So I have made that plot, is it in there?
Sure.
Yeah.
Alright, I think we do need to wrap up because we're getting right towards 1 o'clock, but I'm sure there's a lot of more discussions that can happen, so if you want to find Hamish afterwards with additional questions, that would be great. So otherwise, thank you all for coming, and we'll see you next week.
Sweet.